All right, let's play detective for a minute. But forget the shadowy alleys and crime scenes. Our mystery is inside a power grid, or a factory, or even a massive piece of software. Our job? To hunt down that one tiny fault that's brought the whole system to its knees. So let's grab our magnifying glass and get started. You know that feeling, right? The website's down, the power's out, your flight gets delayed. Somewhere deep inside a system with literally millions of parts, one little thing broke. But finding that one thing, well, it's like trying to find a specific needle in a haystack the size of a continent.
I mean, really, put yourself in that control room. Red lights are flashing everywhere. Every single alarm is just screaming at you, and they're all giving you conflicting info. The pressure is on. So where do you start? The power supply, a line of code, some random sensor in the middle of nowhere? The sheer complexity of it all is just completely overwhelming.
Now, there's a fancy engineering term for this kind of detective work. It's called fault detection and isolation, or FDI for short. And it's really a two-part job. First, there's detection. That's the easy part, just confirming, yep, something's definitely broken. But the second part, isolation, that's the real challenge. That's figuring out exactly what broke and where it is. That is the mission. So how do the pros cut through all that noise and chaos? They don't just start pulling levers at random, no. They have a secret weapon. It's a special kind of map that lets them ignore all the clutter and see what truly matters. Just try to picture it. A modern factory has miles and miles of wires, hundreds of machines, thousands of sensors. Or think about a power grid, this dizzying web connecting millions of homes. If you look at it, it's just a tangled mess. Trying to understand it all at once is basically impossible. And right there, that's the big aha moment. What if we just stopped looking at the physical machines, all the nuts and bolts, and instead, we just focused on how they talk to each other? It's not about how big the pipe is, it's about the fact that it connects the pump to the tank. It's all about the flow of information, the connections. This is where our secret map comes from. It's called graph theory, and it's just a brilliant way of simplifying everything. Every important component, like a pump or a server, becomes a simple dot. We call that a node. And any connection between them, a pipe, a wire, whatever, that just becomes a line. We call that an edge. And just like that, the chaotic, messy factory floor turns into a clean, simple diagram. And here's what makes this so incredibly powerful. In the real world, things are messy. We don't always know the exact pressure on that pipe or the precise voltage on that wire. But this map, it works anyway. It focuses on the basic, fundamental connections, which gives us amazing diagnostic power, even when our data is messy or incomplete. That's a huge deal. Okay, so our detective has the map. Now let's see how they actually use it. Time to open up the case files and solve a few system mysteries. So this map isn't just one tool. It's more like a whole diagnostic toolkit. For those really complicated systems where everything is interacting in weird ways, there are specific methods to untangle that knot. To figure out if the clues you're getting are even reliable, there are ways to double-check your data. And for massive spread-out networks like the internet, well, there are special tools for that too. The map adapts to the mystery. All right, our next case isn't about solving a failure that's already happened. This one is all about getting ahead of the problem. You could call it proactive detective work. It's about figuring out where to place your surveillance equipment, or in this case, your sensors. And the strategy here is just so logical, it's beautiful. First, you create a really detailed blueprint of your system, something engineers call a bond graph. Then, you take that complex blueprint and you turn it into our simple dot and line connections map. And finally, you analyze that map to find the most critical intersections, the most important pathways. And those are the most strategic spots to place your sensors. And this just shows you the night and day difference. Before, putting in sensors was kind of based on educated guesses, right? Which meant you could have huge blind spots. You'd only find out you were missing a sensor after something expensive broke. With graph theory, it's totally strategic. You place sensors with surgical precision. You get full coverage, and the whole system is optimized for a super fast diagnosis. So we've seen how this map can help us track down a single fault. But its true power, well, it goes a lot deeper than that. It allows us to understand the master blueprint of the entire system on a really fundamental level.
And this is the key takeaway. We're moving from being a reactive detective who just solves crimes to being more like a profiler who understands the system's very nature, its personality even. It's about asking the big questions before anything has a chance to go wrong.
This whole approach lets us analyze a system's DNA. We can figure out its diagnosability, which is just asking, hey, if a fault happens in this specific part, is it even possible for us to find it? We can check its observability. Can we actually tell what's happening deep inside the system just by looking at the outputs? These aren't just questions about one failure, they're about the basic design of the whole thing.
You know, there's a quote from the source material that just sums it all up perfectly. These tools let us analyze inherent systemic properties. That's the system's DNA we were just talking about. And doing that is a prerequisite for success. In other words, you have to understand the underlying structure first before you can ever hope to manage it when things go wrong.
And that really leaves us with a fascinating question, doesn't it? This powerful way of seeing the world isn't just for machines. The exact same ideas can be used to map the connections in a social network, or the flow of money in an economy, or even the pathways of a disease. If you can see the hidden connections, you can understand almost any complex system. So the real question is, what should we map next?